All right, guys. Before we start, I guess I also posted the next part of the project. I'm not sure it's 5 or 4. Let me see. It's 4, right? So this is your sewer design. And let me see here. Just look at few things. Wow, that's not showing.
You probably download it and it'll show faster. Canvas a little slow today.
Yeah. It's not heavy one anyway. Everything is slow. Too much traffic, I guess. Right? Oh, there you go. Okay, guys, this is your project. You are trying to design the submain sewer at street number 3 from manhole 4 to manhole 19. This is it. This one here. You start from manhole 4, go to 8. This is the first segment. Then from 8 to 13, the second segment. And from 13 to 17, the last segment. No, still, from 17 to 19, that's your last segment. Okay. You see topography here, right? And you need distances. Okay, I gave this to you. We'll see down the road. Now, before we go, this submain gonna collect everything that comes from this lateral, from Avenue A. And this goes to manhole 4 and runs this way. Now, at this manhole 8, you're gonna add everything that comes from this side of Avenue B, plus what comes from Avenue B from the other side. And this gonna run in this segment until you get to 13. 13, you have lateral from Avenue C from this side and Avenue C from the other side. And everything gonna run in this segment. At 17, you're gonna have what comes from Avenue D from both sides, and everything gonna run now to the 19 here. Make sense? The layout of this community. Okay, now we need to figure out how much Q gonna run in each of these laterals. Well, this depends on how many people live here, per capita, and how much wastewater they generate. Let's see here. Okay, you need to show your result spreadsheet and profile exactly as in the handout. Remember I told you about this last time? Do exactly the same. Don't change anything in the position of the columns or the rows, all right? Same column, keep it that way. Now, the average daily generation of wastewater per person, per capita, which means, is 85% of your average daily water demand. So you need to go back to your water daily demand that you did in the beginning per person, per capita, and multiply that by 0.85. This is going to give you how much wastewater per capita per day. Well, that's the average. We work with the peak. You multiply by 3. All right, this is per capita. Now, you don't know how many people live in there, right? Well, I give you here some of them. On Avenue A, you have 228. In Avenue B, 624, both sides, C and D. So these gonna enable you calculate the peak flow in each lateral. Make sense, guys, or not?
Yes.
Okay. Now, surface elevation at manholes, here are they. So you need to follow these numbers. And the distances between manholes is given here as well. So elevations are known at 4, at 8, at 13, at 17, and at 19. And the distances between them are known. Q in each lateral is known. So, or you can calculate it in other words, right? So you don't have problem. Start with this one here for, this is your first manhole, okay? And as we agreed, when you start with the first manhole, make sure that you have 1 meter coverage. The cover 1 meter, right? Don't go deeper than that. You don't have basements. 1 meter cover plus the diameter of the sewer. This gives you the invert at the beginning. Okay. Now the slope, you know the rest of the story. Follow the table and the calculations in the handout. You know, this is the surface elevation. So the difference between them divided by the area gives you the slope. Try the same things, you know. Slope of the sewer equals the slope of the surface. If it gives you cleansing velocity that is at least 0.6 meters per second, flowing partially full, you are in the safe side. Otherwise, increase the slope. Okay, and keep going. It's very easy, just one sewer. I didn't make it more. Usually, I give this, the design plus this. All right, guys, and guys, please make it in SI units. Everything is in meter cube per second. Velocity is meter cube, meter per second. Okay, meters, metric system. Okay, guys, if you don't have questions regarding the, oops, the project, then we can go ahead and start a new subject. All right. Okay, what do you think? You finished with your wastewater collection system. What's next?
Treatment plant.
Wastewater treatment plant. Thank you. In other words, you got okay. Now what? In other words, you brought your sewer throughout the community. Let's say that. Just simplify it, you know, simplify it. All right. And here some kind collector. All right, collects from here also as well. And you brought it here. Let's say this is the interceptor, the last one. All right, this is the interceptor. The last trunk, okay? These are lateral submains or mains, and this is the trunk, whatever you want to call it. And your wastewater treatment plant is here. You choose a location. Okay, your wastewater treatment plant here. And this is the end of that interceptor, right? What's going on? At the end of the interceptor, you have a manhole. Big one gonna be, right? Manhole. So it depends where is your ground surface. And here there is a manhole. Right? Sometimes they call it the wet well. It's a manhole, but it's big one, all right? And the wastewater comes here. Now you have fluctuation in elevation here. You understand, you know, the flow that is coming is not the same, you know, all day around. It fluctuates. It depends how you use wastewater, how you use water at home. Maybe use it during the morning hours more than the afternoon, which is true. And use it in the evening more than midnight. So there is some kind of minimum. Let's say that. And let's say max. And there is somewhere average if you want. Okay. Now, this elevation is below the elevation where your wastewater treatment plant gonna start. So your wastewater treatment plant gonna be located somewhere. Here is the ground surface. We got it that way. And at a given point here, we call it the stilling well, still water is still. Or basin or tank, you need to pump this from this wet well here, all right, to a given elevation here. Why is that? After that, your wastewater should run through different kind of facilities and equipment in the wastewater treatment plant by gravity. Okay? By gravity. So this is kind of calculated. We calculate this thing that is called the hydraulic profile of the wastewater treatment plant, right? It accounts to all losses that happen in different kind of facilities, equipments, and so on. All right, so you run it by gravity and you make sure that this is a command elevation. It enables you to get this kind of pressure here, H, minus all H losses, and you will stay in the safe side, you know, positive. You stay still positive. In other words, what we are saying here that the sum of H losses, whether it's friction losses or local losses, should not exceed this H in the beginning of the wastewater. Okay, let's see here. Now, you need to pump this from this wet well to that stilling well. All right, this is the first thing to do. This is what we call the headworks. No treatment yet. Okay, so you pump it here. Now, before you take it to anywhere, you need to install some bar screens. Okay, it depends where the water gonna flow from the stilling well. Depends. Let's say flows from here. So this is gonna be your bar screen. That's to remove any debris, right, and big objects that if otherwise they're gonna cause some harm to your equipment. right? And pipes and gates and other things. So you remove these debris. This is also part of the whole headwork. Okay. This is needed. What needed also is a measurement. You need to measure the flow. Okay. You need to measure the flow. Always measure the flow in it. Merely we use partial flume. Similarly with these pumps, because wastewater has objects in it, big ones, small ones, middle, medium, you know, different kinds of impurities, different kind of trash in it. We use open, right, devices here, not closed ones. Closed ones are not effective. Even the pumps are open. They are atmospheric screw pumps. You will see down the road. Same thing for the flow meter. We use partial flume, open channel. Okay. So you need that as well. And you need screens. Screens also always in open channel installed. Then after that, you take everything to the preliminary treatment, which is actually the hoodwork plus the grit chamber removal. Grit chamber. This removes grit, dirt, small particles of whatever, silt, sand, coffee ground, right? Tiny objects, mainly non-organic stuff should be removed. Grease, oil, right? Grease and oil gonna float on the top, and they remove it. And these small, tiny silt, clay, sand, coffee ground, you know, all these tiny things gonna somehow they force them to settle to the bottom of the grit removal, and they remove them from the bottom. And most of these grit removals in modern days, they are aerated, right? They pump some kind of air, spiral air inside them. And you're gonna design this as well. Okay, guys, so this is what we are going to discuss. Headworks and preliminary design, the grit removal. Right after that, you're gonna go to the primary design, which is the primary clarifier. Then to the secondary, which is the biological treatment. That's your aeration tank, and you did this before. With the secondary clarifier, they come together. All right, and the last thing is disinfection. If your if your plant is advanced one, then you need to add a tertiary treatment, chemical treatment, where you polish the water more. You remove phosphorus and nitrogen compounds, okay, and refine the water. It becomes almost drinkable, you know, potable water, almost. If you add more filters, fine filters to it, you know, microfiltration or something like that, you can drink it. Okay, so this is what we are going to look at today. The hardware, screw pumps, partial flume, bar screen, and grit removal. We'll talk about equalization tanks, but we are not going to design them. Okay. Equalization tank, you need it because inside the water treatment plant, you know, your Q must be constant. Given Q for your operation and for the design to begin with. However, Q that comes to your plant fluctuates. So you need this equalization tank here, all right, to store water that is exceeded. And here, from here, you go constant Q. See, straight line, constant. And this happens, you cut this fluctuation, in this equalization term. Okay. Okay, we are familiar with this, why we need a wastewater collection system and why we need, okay. This is a good idea. You understand what's going on here. What do you mean by wastewater treatment? What do you mean by sewage? Wastewater, what is wastewater? Wastewater is like water, right? If you have 1 cubic meter, 1 cubic meter, 1 cubic meter, 1 by 1 by 1, 1 cubic meter of wastewater, it is the same as water, almost. It's 1 ton, which means 1,000 kilos, 1,000 kilos. Okay, same as water. Now, inside this 1,000 kilo, you have about 0.5 kilos solids. That's it. In other ways, most of the wastewater is water. And this is from where we get that old wisdom. You know, wasting water is such a waste. You don't waste water. Why you have to waste water? Almost all of it water. Why you need just to waste it somewhere? Unclean. Clean it and use it. This is the whole idea. If you don't want to use it, at least you discharge it in water, but it's clean, not polluted. You don't pollute wastewater. Sorry, you don't pollute natural water bodies, especially United States. That's the Clean Water Act. Nobody has a right to pollute the waters of the United States. Okay. So from that point, all right, from that 0.5 kilogram of the solids, all right, half of it, which is 0.25 kilos, 0.25 kilos of that solid is dissolved, such as sodium, nitrogen, some organic, dissolve, right? The other one is not, right? Not dissolve. However, these, half of it can settle out and half of it stays suspended. Okay, 125, 125. So these can settle, these still suspended. Okay. So based on this, in wastewater treatment, we deal with things like the total suspended solids. Total solids, you know, we discussed this maybe last semester. So these are some kind of the characteristic total solids. Here it is. Total suspended solids here, right? Total dissolved solids here, some of them. So it depends what you want. But these are the most two factors that work well. BOD, right? BOD soluble, here are part of it organic in this part, right? BOD. Nitrogen compounds, phosphorus compounds. These characteristics of the wastewater give you how strong is it, all right? The strength of it. This number, mainly BOD. Okay, here are some examples, how strong. United States, look at this, for example, here. 200 BOD. This is not treated, it is raw. All right, total suspended solids, this is per liter. Suspended solids, nitrogen, phosphorus, sorry, phosphorus here. total and soluble. Okay. BOD, you need to remove it. You need to remove suspended solids and total solids. Settle out. This is why we have primary clarifier, and after that we have another one, secondary clarifier, to move these guys from here. All right. If you need to move nitrogen and phosphorus, that's a good idea. This can be this can be done in the same tank here, the aeration tank. Okay, it's a good idea to remove them. These are nutrients for plants and algae, right? If you leave them in high concentrations and you discharge your wastewater with high nitrogen and phosphorus compounds to the natural water bodies, you encourage the growth of algae, right? The growth of algae gonna make a green layer on the top of the water bodies. And eventually this algae gonna overwhelm that water body and prevent light from penetrating through. This eventually gonna kill that water body. So it's a good idea to remove them or reduce them to some acceptable concentration. Okay. So this is what you got. This is the raw that comes to your wastewater. Okay. Not strong much in the United States. This is because we use too much water. We flush a lot. And we use water a lot for showering and cleaning and washing. In other places around the world, they don't have that luxury. See here, Kenya. See how strong is it? Even United Kingdom is stronger than United States. We don't use as much water as we do. Okay, guys. Now, based on this, right? Based on this, you're gonna design your wastewater. It's the influent, how much strong it is. The flow rate, how much of it comes to your wastewater plant. And the effluent, what's the recommended values? We'll look at them now, all right? Are you going to go with 30 milligrams per liter BOD or 20? Or maybe you're gonna go advanced. You wanna go with advanced treatment, this number must be more, maybe at 5, right? Or at 10, depends. All right. So in your wastewater treatment plant, you have 2 trains, right? 2 processes, in other words. One that deals with the liquid, here it is, all this one here, liquid. And because you have dirt, we call it sludge, you have another train to treat the sludge as well before you take it to wherever you want to take it, landfill or somewhere else, right? Some places using anaerobic bacteria in the digester to produce methane gas, and they use it as energy for the plant. They do that. Some they don't do, just to use the aerobic digester, and from there they take it to some kind of thickener, right? Squeeze out water and make it thick, and then after that take it to landfill. All right, 2 trains. All right. As I said, you don't have the right to pollute the waters of United States, right? Whenever you have your wastewater treatment plant, you need to get what we call a permit. It is the National Pollution Discharge Elimination System permit, right? You take that either from EPA, Environmental Protection Agency, or your local authorities. You need a permit to discharge the water from the wastewater after you clean it to the waters of the United States. When we say permit and you need to discharge into the waters of the United States, they need to make sure that you are discharging quality water, right? And this is going to be upon required based on that permit, what you give them and what you agree with them. You tell them that I'm going to discharge this quality of water, BOD, right? COD, nitrogen, phosphorus, blah, 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 you know? And you agree with them on these numbers. They're going to inspect it from time to time. Okay, here are some numbers for United States. All right, this is mostly used. If you want to go advanced, see the BOD advanced, you drop it into 5. Total suspended solids, 5. Total nitrogen, total phosphorus, very low numbers, almost drinkable water. If you do disinfection, you know. Okay, so stages. Pre-treatment. Pre-treatment, we mean by that, if you have any industry, all right, or commercial maybe, or lab, or whatever, and they want to connect to your wastewater collection system. In other words, if you have any industry, let's say here, and they want to connect to this sewer, all right, this is not the master industry, which means they have their own pollutants, you know, that usually doesn't exist in wastewater that comes from houses and other places, you know, let's say hospital or something. Now, this thing that they're gonna use, whether it's chemical or toxic material or whatever, gonna run with the sewers and eventually comes to your wastewater treatment plant. All right. However, your wastewater treatment plant is not designed to treat their waste. This is very dangerous. So to allow them, to give them the permit to discharge into your wastewater collection system, the municipal one, let's say that, they have to make their own pre-treatment here in their facility. Make sense? And this is very specific. How they do that, this is their problem. Okay. So you finish with this. Now you go through the preliminary design, as I said, primary, you remove the solids, and the dissolved, which is the biological treatment, all right? And you remove then the other train, biosolid disposal, trash, and so on. All right. Let's look at this video. Just it's one of a few series of videos. It's a very good one, actually. Let me see if I have it here somewhere. Yeah. Okay, guys, let me try to share this. Oh, sorry, I did a mistake, I guess. Let me stop. Okay, let me see. Can you see this from your end?
It's still loading.
Yeah, I think we can see. Just hit play.
Yeah, if you can see, let me start this then.
Hi, this is Bill Hogru with the Rural Community Assistance Partnership. This is it. This is the end.
Can you see and hear?
Yeah.
Yes.
This is the end, actually. I started by showing you the end of the process. This is a treated water already. They discharge it to water body. Listen to the guy. Go ahead.
The Rural Community Assistance Partnership. This is it. This is the end of our treatment. We've gone through our preliminary, our primary, and our secondary treatment. We've done our disinfection. We've got our contaminants out, got rid of our pathogens, and it's taken about 12 hours for a drop of water to go from the beginning of the plant to this point where we discharge into the creek. During the entire wastewater treatment process, water spends a few hours in the primary clarifiers, about 5 hours in the aeration basins, and a couple more hours in the secondary clarifier and chlorine contact. The total flow rate for this plant that serves about 150,000 people is about 20 million gallons per day. In 12 hours, that's 10 million gallons. That 10 million gallons would cover an area a little larger than 2 football fields to a depth of 10 feet. You can see the stream is actually more turbid than our effluent because there's been some rain upstream. The water from us goes back into the stream and it's used by people downstream for drinking water, for irrigation, and for fish and for recreation. Our water's clean enough where we can send it in without damaging aquatic life, and we protect the public health of the folks living downstream from us that use this water for drinking water. So the reason why we put all this effort into treating the water and getting it back to its pure state before we discharged it into the river is because all life on Earth depends on water. And so it's worth the effort that we put into it for future generations and for all the folks that live downstream. This is Bill Hogru for Rural Community Assistance Partnership.
Okay, guys. Sense now why you need that treatment?
Yes.
Okay, how many hours wastewater stays in the wastewater treatment plant in this one?
12.
12 hours. Took 12 hours from the beginning to the end, right? And how many people it serves?
Is that 120,000, 150,000?
Yeah, kind of that. Yeah. How many gallons you remember?
I think it was 20.
Yeah. You think I have window update? Oh, yeah, I have one. Right, right. All right. How did you know that?
There's an icon in the bottom right corner.
This one?
Yeah, it's got a little it's like a
Yeah.
refresh sign. Yeah, Windows updates, they're not that great. You don't have to worry about them. But it could help your computer maybe
Okay, I'll do
for
this.
security reasons or something. I don't know.
All right, I will do this when you finish. Thank you. Okay, turn caption for videos. I'm not sure if I have caption of mine. Okay, so let's go back then. You understand now what's going on. Okay, and Chani, who's Chani?
That's my transcriber.
Okay, all right. I'll send you a private. Okay, guys, so let's look at the headworks, all right? Preliminary treatment, the most important thing in it is the grit removal, as you see here in this drawing. You need a bar screen before that. This is your raw stuff, all right? So this is the preliminary treatment, okay? Bar racks, grit chambers, equalization tank, primary settler, that's a primary one. Here, how you need that equalization basin. See here, equalization basin. Flow is constant after that. Before that, the flow fluctuates, all right? So it's a good idea to install some kind of flow meter after you finish with the equalization. And here, also as it comes in the headwork here, you need a pump, as I said, plus flow meter. Sorry. Okay. So this is what we are going to discuss. Let's look at these pumps, screw pumps. All right, this is what you have. Here it is. You know, this is actually a wastewater treatment plant. You have 3 pumps. See here, this is the last point of your interceptor. Okay, this is a wet well. And you see that the pumps are going down to the bottom of it. And here somewhere, you have the stilling somewhere here beneath after these. The kind of stilling basin, all right? This is where you're gonna start your hydraulic profile. This is from where wastewater gonna start running through the wastewater by gravity. Okay? And we call them screw pumps because they are screws. And they are open, you know? And there is huge distances, you know, between them. So if you have big debris, no problem. They will not clog them. They are non-clogged. All right, high volume. Their problem is the efficiency is low. Well, they are open to the atmosphere, right? So that's not a big problem, right? They can carry kinds of different kinds of debris. This is why we like them. This is your first step to lift your wastewater from the interceptor, from the manhole up to the beginning point of your wastewater treatment plant. all right? These comes from manufacturers. You don't need to design them. You need to select one, all right? However, they come in different design. They come one flight, see one flight, the distance between the screws is large. Then they come two flights, kind of another one here. And they come three flights, kind of another one here. So, as you see, right? The lift here, which is H, the static head, it's the difference between the minimum point in the interceptor and your delivery point here in the steering wheel, right? You need always one Corey. We don't see as well when one of them is out of order, right? You need another one always. So the task here is from this catalog is to figure out one of them, right? Based on the capacity, that's Q, and based on the head, that's it. You choose one. Then you need to figure out how many of them. Number. How many you need? Well, also this is gonna depend on Q. All right. Okay, let's write these numbers and we'll go with them and try to find one. This is the minimum sewage elevation in the interceptor. Write this down. All right. Minimum in the interceptor. Maximum into the interceptor. This is the fluctuation. This is the minimum here. And this is the maximum. Steering wheel, this is where you're going to take them. You're going to take them to this elevation. Your average at design capacity is 37 meter cube per day. Convert that to hour because the catalog goes with hour. All right. Just have these numbers. What do you think? What's the first thing you can calculate here?
H.
H. And it equals?
Discharge elevation to steering wheel minus minimum sewage elevation.
Yes, using the minimum. All right, so that's your 519.7. This is how much you got here. The highest point minus the lowest point, 514.75. And this is going to be your H in this case. We know this. How much is that number?
4.42.
Okay. What's going on with this? Oh, not responding. 1 second, please. That's 4.42 meters. That's your H. At least you need a pump that would supply you with such static head? Okay, man, come on. Stop. That's good enough. Now, if you go to that catalog, I'm trying to get there. My PowerPoint is not responding. Okay, let's stop sharing. Maybe it's gonna make it easier. Okay, let me try something else. I'm not sure what's going on with these guys.
What happened, Dr. McDaddy?
My PowerPoint is not responding. Something
Can you
wrong.
close it? Just open and
I'm
close
trying.
it.
I'm trying. I'm trying to open another one. Let me see. Okay, let me try to open another one. Okay. All right, this is better, I guess. Okay, guys, let's go back. So it is, the head is 4.42.
Yep.
Yes.
So see here, this works. Everything here around this area is okay. However, you need to judge with the capacity here. This is maximum capacity given, all right? So we need to figure out what's the capacity here, right? So we do that with respect to the Q minimum, all right? You need to satisfy Q minimum, you need to satisfy Q peak as well, both of them. Now, based on manufacturing of these pumps, these are low efficiency ones, right? You need to calculate your Q, right? So we are giving Q average, I guess. Let me get that number. What's Q average? This one, 1542. Is that average? Yeah,
30. Yes.
1542. Okay, let me go here. So Q average, okay, Q average, this is what we know. 1542, that's meter cube per hour. Is that correct, guys?
Yes.
Now you need Q minimum and Q peak. All right, these you need factors. You know, you understand that, right? Factors. Now, according to some recommendation based on that Q average population served, I think here I took 0.28. And this, I think, 2.8, almost 3 times the average. Check that, please. Is that correct? Q minimum and Q peak.
I think it's a little more than 0.28, maybe point.
Yeah, 432. That's correct. This one. This one. It's not 2.8, maybe. But 4317. Yeah, 4330, maybe 3. Anyway, around these two numbers. All right, this comes from different recommendations. Actually, I show you one last time, one of the graphs that you can use for these factors. If they are not given, usually they are given. So whatever, if they are given, they are given. If not, they give you some kind of chart to find them from there. All right. Now, you start with the Q minimum, all right, this number. Okay. In other words, we are saying that one pump should be able to give you this Q minimum. All right. Now, the problem is these guys, these pumps, when they run at 60% efficiency, they provide you with 30% of the Q, 30% of the Q only. All right. If they run at 60% efficiency, very low, yeah. Okay, so what to do here? This should be divided by this number. I'll explain why divided now. 5.3, how much is this now?
1443.
1443? Yeah, that's correct. Now you ask me, Bimi, why is that? This is because of the following. If you choose a screw pump that gives you this flow rate, and it would run at 60% efficiency, which means it's gonna provide you with only 30%, it's gonna give you your Q minimum. In other words, to get your Q minimum, you need a pump that is much larger than Q minimum. Why is that? Because it's gonna give you only 30% of it. Make sense?
Yes.
All right. So that's your Q. Now, based on this number and based on H equals, how much you said H? 442?
Yes.
You go to there and you try to find that your pump, all right? So let's take these two numbers and go back to the catalog here. 1443, all right? Look, all these numbers up to here are less. This is much more than 1443. This is close. Is that correct, guys?
Yes.
Maybe this is better choice than this one. However, you check also with H. So if you use this one, it's one flight. Be careful. So this one flight. This is the head. Is that more than 442?
Yeah.
Okay. Similarly, this one also 4.9, which was also more than 442. So both are okay. 3 flight and 1 flight can do the job for you. This is too much higher than the 1443. So I would stick to this one. And I tell them I need a pump with a diameter 152. Okay. And this is what we call a Q catalog.
Dr. McDaddy,
Yes.
I know you already passed this part, but why did you divide it by 30%?
Because the Q minimum that I need is 433.
Correct.
Now, these
And
pumps don't run on the 100% capacity. They run 30% capacity of the flow rate.
okay.
In other words, if I want to order a pump that is, this is the catalog, then it will not give me the 100, which is the 433. It's gonna give me 30% of it only. And that's too much less than my minimum. So I need the one that has much higher Q. And when it gives me 30%, it's gonna give me this number.
Was the 60% a typo then?
No, it is when they run at 60% efficiency, they provide 30% of the flow.
Oh, okay. I get it.
Forget about the 60%.
Okay. Okay.
This is what they say about that. All right. Now, this is very technical stuff, and it depends, to be honest, on the manufacturer. So when you look at their catalog, you will see what they say inside it, and you follow what they say inside it. You know, but generally, these are the numbers in general form. Okay. Now, don't forget that you are not working anymore with the 1443. You choose a pump, and this is the catalog. Q equals 1486. All right. So one pump gonna give you this flow, right? Has this flow, but it will give you this flow at minimum. All right. Now, What do you think? How are you gonna find how many of them to meet your peak? Now stick to the catalog. All right? Stick to the catalog. How are you gonna find them? How many of them do you need? Is this the peak? Try divide this number by this number. Are you getting 3 pumps? Q peak divided by Q catalog or Q minimum. It's gonna be close.
Yeah, you end up getting 2.91.
Yeah, you
Which
choose
is-
3
yeah,
pumps.
Right.
And you need one redundancy, as we said. So you order 4 of them. Okay. You order 4 of them. You check for 2 together. Are they giving you your average? Let's say that. You don't need to do this, but it's a good idea to check with the average as well. Okay, guys. In 40. So do you know now how to choose or select a pump?
Yep.
Yes.
All right, now the water comes from this pumping, goes to the settling wind, then it starts running in an open channel, concrete open channel, right? And the first thing you need to do is to measure that flow because it has debris and different things still in it. The best flow meter is partial flume. Partial. Ralph Partial, American engineer who came up with this idea. We call them flumes, right? Open channel. The whole idea is you have an open channel. This is from top view. This is the profile. The idea is if you make it a little bit narrower here, you increase the velocity. Make sense? When you make it narrower, you make your cross-section area less, and this would increase the velocity. And to increase the velocity more, you make this kind of increase the slope in the floor at the same location where you do the narrowing. And this would increase the velocity as well because you have more slope. So by doing that, you increase the velocity kind of twice by narrowing and by increasing the slope. And you understand the flow here is subcritical. When you increase the velocity, the flow becomes what? Supercritical. Between them, you have what? The critical flow. Critical flow is, or the regime is between water goes from subcritical to supercritical. At that point, you can apply the Weir formula. U equals some coefficient C, all right, times the head of water approaching the critical times or raised to N, all right? You had this in hydrology and hydraulics. We had different numbers, depends on what kind of weir and so on, all right? This is the Weir generic formula. So this is the whole idea with these flumes, all right? Dr. Ralph Marshall designed many of them, all right? They are standard now in the United States. And they are standard based on the throat. We call it the throat, this narrowing throat, W, the width of the throat. So if you know the width of the throat, you know everything else in it, okay? So this is the whole idea now. Here are they. This is the throat. And that throat depends on the range between minimum and maximum flow. This is how you choose them. All right? This is how you choose them. Meter cube per hour. Remember what was our minimum? I think 433. And what was our maximum? 4330, right?
Yeah.
All right. And 4330. This is a range. You need to fit that range between these numbers and this number. Can you fit it here?
Nope.
The answer is no. Here?
Nope.
Here?
No.
Here?
No, no, and no.
Here?
Yes.
Okay, so your 433 is more than the 100, and your 4330 is less than 5100. So this is the one that you need. And this is your throat, W. Good. All right, remember this number, 0.91. So Q, the flow rate, equals C times H approach raised to N, correct? Now we need the coefficients, right? We need the coefficients, where are they? Here are they, sorry. 0.9, we said, the throat?
Yeah, 0.91.
Yeah, take this number from here, please, whatever you like. 1.57, that's N. Good. Take this number. 2.5, good. For C.
Yeah, looks good. 2.5.
Okay, calculate Q peak. All right. CH B raised to N. If you have your Q peak, how much was it? 4330?
Yeah.
Yeah, they usually calculate it for Q peak, go average and minimum. You need to know the elevations in that flume that you're just gonna order. You need to know the depth of water in it at different Qs that you have at your peak, which is gonna be the highest, at Q average and Q minimum. All right. Put these numbers. You said this is 2.5 or so. H approach, or whatever you want to call it. And this is raised to how much we said this one?
1.57.
1.57. And you calculate that H at the highest. This is the elevation gonna be inside it at the approach. You see how much I got here. Here. 3 board 0.6. Okay. And repeat that for Q average and Q minimum as well. In other words, inside this flume here, you're gonna know this one here. This equals 0.63 at peak. Then it's gonna equal another number at average and another number at minimum. Three numbers. Okay. So far you got your pumps, you got your partial flume. We need then from partial flume to design the open channel where you can install your bar racks. All right. And after the bar racks, you need to design your grit removal. Okay. We'll do this next time. That's enough for today. Okay, guys, if you don't have do you have any question, guys, or we can stop here?
No questions.
No questions? All right, you enjoy the rest of your day then. See you.
Thanks, Professor.
Have a good
Sounds good.
day.
You too.
Thank you.